Okay, so I'm very happy to introduce yet another speaker in the historical paper series, seminar series, that is organized by Daniel Weeks and Vinod Vaikutanathan. Daniel's here, but where's Vinod? Okay. And all these talks are being recorded, so you can watch them all online. If you've missed a few, you can see them. So it's a pleasure to introduce Dan Boneh, who is a professor at Stanford. And Dan is a very unique person in our community. There are a few, but maybe a handful of people like Dan who managed to combine both an excellent level of theoretical research in computer science and an excellent level of research in the practice, and not just research, but also implementation of things and so on. Our field is in great debt to Dan for introducing the notion of wild pairings, not the notion, into cryptography, and implementing with it the notion of identity-based encryption. And that result, the introduction of the bilinear maps, really created a revolution in our field. The number of citations that this paper has and the number of papers that have used this technique is simply tremendous. He is also responsible for the microwave attacks, which are a paper which he did while he was in Princeton, which really set off the field of tampering in order to extract cryptographic materials, and really also another area that flourished tremendously over the years. And he also had the scheme with Go and Nissim of having the first crypto system that had, you could do as many additions as you wanted in a single multiplication. And I think that that result really kept the hope going that we would eventually be able to find a fully homomorphic encryption scheme. And I think that Dan nurtured this idea all throughout. And on the practical side, I wanted to give an example of something that he does, which really exemplifies the fact that he has all these ingenious ideas, not only in the practice, also in the theory, but really beautiful ideas. So he has this password scheme that the idea is that you, despite knowing the password and being able to get into the system, that you would not be able to transfer this information to yet another person, which seems a little bit paradoxical. But his result manages to achieve something along these lines. It's really beautiful, and many of his works have these ideas that you say, wonderful. And he contributed, he's raised a generation of students. I think at any given time he has about 50 students. That's a little bit of an exaggeration, but really a lot of students have come under his instruction. And he also teaches courses in Coursera, which is the online education, and they're really amazing classes. He's an amazing teacher. Of course, his work has not just been noticed by us, but also has been awarded by the community a lot of awards. The Gödel Prize, the RSA Prize, the Packard Prize. He's also an ICR Fellow, and this is just to name a few. And to finish with a little story, which is not research and so on, it was clear that Dan would be a cryptographer because he attended the first crypto in Santa Barbara, which is a true story. You might be surprised, but the truth is that he was a child living in Santa Barbara at the time. His father was at the university, but he was there present, and from there started a great career. So please help me welcome Dan.
Boy, so I'm really blushing, Tal. Thank you. I don't think I've ever heard an introduction like this, so thank you. In fact, I should probably just end the talk right now and declare victory. So thanks for the introduction, and thanks for inviting me to give a historical relic talk. I don't think of myself as a historical relic, but so be it. I would have actually enjoyed to talk about more recent work that we're doing, but I guess I'll do that some other time. For now, I guess I'll talk about the history of pairings and where they come from, where they've been used, and so on. Before I get started, I want to kind of thank everybody for finishing up your TCC submissions on time. I guess the submission server just closed, so everybody is probably dead tired, and you're probably thinking about the commas that you forgot in your papers and the little I's that you left out and the subscripts that you got wrong. So in this hour, I think what I decided to do is focus more on stories and not torture you with lots of proofs. So hopefully this will be a light talk. Hopefully. I'm not sure I succeeded. So yeah, we'll see how it goes. All right, so with that, let's get started. So I'm going to talk a little bit about how pairings are used in crypto. Basically, again, as I said, where pairings come from and the impact that they've had. And potentially, I'm going to try and outline a bunch of open problems. And I hope I'll inspire you to work on these open problems. And I think there's a lot of progress to be made. Some of these are open problems on pairings. Some of these are open problems in the sense that we can do something with pairings, and we'd like to do it with LWE, but we don't know how to do it yet. So hopefully that will inspire you to come up with LWE-based constructions. Okay, so that's kind of my goal, and hopefully I'll get through everything. So we'll see how it goes. All right, so let's start at the beginning. So in the beginning, there was the Diffie-Hellman protocol. So as you know, Diffie-Hellman, of course, works in a group of prime order. It's a famous protocol, sending G to the A and G to the B and getting the secret key. The shared key is G to the AB. Security of the Diffie-Hellman protocol, of course, follows from the decision Diffie-Hellman assumption. So it should be the case that this G to the AB is indistinguishable from a random element in the group. Okay, so we all know and love the DDH assumption, and we've done a lot of, there's a lot of consequences and applications to the DDH assumption. And more generally, we kind of state these complexity assumptions in the group G. These are just kind of the standard complexity assumptions that we know and love, right? So we'd like the discrete log problem to be difficult. So given G and G to the X, it should be hard to get X. We'd like the computational Diffie-Hellman problem to be difficult. Given G to the X and G to the Y, it should be difficult to get G to the XY. And as we said, we'd like the decision Diffie-Hellman problem to also be difficult. So again, these are kind of standard complexity assumptions that we all live with every day, and we make lots of uses for them. The first question is, in the Diffie-Hellman protocol, at least in the abstract Diffie-Hellman protocol, the first question that comes up is, which group G should you actually use, right? What is the group that we instantiate with? Of course, Diffie and Hellman, originally when they wrote their paper, they instantiated their protocol using a group that's defined over a finite field. So they used the group FP star. So this is all nice and fine, and this works well in practice. The only problem with this is the discrete log problem in FP star is not as hard as you would like. As you know, there are sub-exponential algorithms that actually break discrete log in FP star. And because of these sub-exponential algorithms, we essentially have to use a relatively large prime to get security to be where it's supposed to be, right? So today people use primes that are on the order of 2,000 bits. The recommendations are even to use primes on the order of 3,000 bits. So these are relatively large primes, which causes the protocol to be slow. So I'm sure you're all aware of this. And of course, the search for other groups has kind of been going on for quite a while. So there are other groups that have a hard discrete log problem in which you can try to run the Diffie-Hellman protocol, right? So you can use extension fields, matrix group, class groups. All of these have been explored for running the Diffie-Hellman protocol. But unfortunately, all of these either have an easy discrete log or a sub-exponential discrete log problem. So again, would result in large parameters and be somewhat inefficient. Or they have a slow group operation, which would again result in a slow protocol. Before we go on any further, I just want to mention this one fact about the class groups, which seems to be ignored. Just maybe this will be useful to you in the future. So class groups are things that have kind of proposed in the I want to say 80s or so, and somewhat died. They're not really used in crypto these days. There's one property of class groups that I think is useful for people to remember. So if you need a group where the group size is unknown, so you want a group of unknown order, the standard way to generate that is you just generate an RSA modulus, and we know that a multiplicative group modulo an RSA modulus has an unknown order, right? Its order is phi of n, and phi of n is hard to compute, assuming factoring is hard. Well, suppose you wanted to build a group of unknown order without a trusted entity, right? Someone with RSA, someone has to multiply the two primes together and publish this random modulus n. So if you wanted to generate a group of unknown order with without a trusted entity, it turns out class groups are a really good way to do it. Yeah, it turns out, yes, these are groups They're very easy to define, and computing their order actually takes exponential time. Yeah. So again, groups of unknown order without a trusted entity. So this is good to keep in mind. Yeah. Question.
So when you say it takes exponential time, we don't know how to do it better.
We don't know. Yeah. So the best algorithm takes actually sub-exponential time, but there is no known better algorithm. Exactly. By the way, an alternative, again, just to drive the point home, if you need a group of unknown order, an alternative way to do it without a trusted entity is to just generate a large enough random number and hope that it has two large prime factors. Turns out you have to generate a relatively big number for that to happen, and class groups are actually a more efficient way to do it. So just keep this in mind. This comes up in applications like accumulators, where you need groups of unknown order, and you can generate them here without a trusted entity. Just as an aside, if this ever comes up, keep in mind that this is something that could be put to use. Okay, so those are kind of groups that have been considered over the ages. All of them are not better than FP star. And the first group that actually has turned out to be better than FP star, of course, is the group of points of an elliptic curve. This was proposed by Miller and Koblitz, where, first of all, the best known algorithm for discrete log takes exponential time. It's square root of the size of the relative prime. So this means, again, that we can use much smaller primes and achieve the same complexity as working in FP star, at least as far as we know. Maybe there's a breakthrough to be made that we don't know about. But today, as far as we know, we can use much smaller primes because the discrete log problem is much harder, and we have efficient group operations. So just there's this famous table that comes out of NIST that says, if you want comparable security to a 128-bit symmetric key, if you're using FP star, you're supposed to use a 3,000-bit modulus. If you're using an elliptic curve, you can use just a 256-bit modulus. So as a result, operations here tend to be faster than operations here. And that's actually gotten quite a bit of deployment. The interesting thing is that for many years, people have only looked at elliptic curves just for their efficiency improvements. Just you can use smaller primes, so things run faster, and that's the only interest in elliptic curves. Just efficiency improvements. It turns out, actually, and that's kind of what spurred this topic, it turns out elliptic curves actually have additional structure called a pairing, and that gave birth to this whole new tool, which I'm going to talk about. Yeah, question?
About matrix groups, do we know sub-exponential algorithms for discrete log?
Yeah, they're basically reducible to kind of finite fields.
I see. Okay.
If you have to restrict yourself to a billion subgroups of matrix groups, and then they're reducible to finite fields. So, yeah, it's a good question. Okay, so this is the reason. So for many years, the structure was ignored. In fact, was viewed as a problem. And the point is that, in fact, this structure is actually quite useful, and that's what we're going to talk about. Before I talk about pairings, I want to quickly go back to this group of points of an elliptic curve and just make a few comments about this. I'm not sure you're aware of everything that's happening today, so I just want to quickly kind of point out a couple of issues with it. So first of all, the group of points of an elliptic curve, again, just as a quick review, what we do is we fix these parameters a and b. These a and b define this equation, this curve, y squared equals x cubed plus ax plus b. And the group of points is basically the set of solutions to this equation. And of course, this is not just a set of points. There's a group operation defined on them, meaning given 2 points, you can add them up and get a third point, and that is a group operation. So this, again, I'm sure everybody, this is just a quick review. I'm sure everybody knows this. I'll just use EFP, E parentheses FP, to denote this group. Okay, so in practice, what do people do? In practice, people use, first of all, a 256-bit prime. That's the only thing that's used in practice, or primarily the prime that's used in practice. The measurements basically show that this is about 10 times faster than using a comparable FP star. And as a result of this 10x speed up, the world is slowly transitioning to using these elliptic curves. It's actually quite remarkable to see this transition. We did it. So, for example, if you look at Google, every time you connect to Google these days, you're actually doing a key exchange using elliptic curve Diffie-Hellman. Yeah, so all key exchanges with Google essentially use elliptic curves, and we actually did a study last year of the top 100,000 websites. If you look at the Alexa top 100,000 websites, we connected to each one of those. We asked what kind of key exchanges do you support, and about three quarters of them support elliptic curve Diffie-Hellman, which means that about 3/4 of the top 100,000 websites will by default use elliptic curves over prime fields. So that's quite interesting. And the other interesting thing is that, in fact, of these 100,000 websites, of the 3/4 of the 100,000 websites that support elliptic curves, almost all of them, 96% of them, use one particular curve. Use one curve called P256 as a name. So you wonder, what is this curve P256? Where does it come from? And let me just quickly show you where it comes from. I hope not everybody has seen this. So this curve comes from a standard. It's a NIST standard. It's in the appendix to the NIST standard. The curve in particular looks like this. This is the structure of this curve. And in the standard, literally the standard says, here is the prime that you're supposed to use. You notice this is a prime of low weight, so the arithmetic is simple on it. This is the number of points on this curve. It's roughly 2 to the 256. So 256 bits, this is the number of points. This is the coefficient b in the curve. And this is 1 point on the curve that you can use as a generator. All right, and as I said, almost all websites use this one particular curve. That's a lot of eggs in this one basket. So the next question you should ask is, well, where did this curve come from? Where does P256 come from? And here the story is even more disturbing in that, again, you look at the standard, and in the standard, in the appendix, there's one magical seed. That seed is hashed using SHA-1, and that SHA-1 hash gives you the parameters for this curve. So the next question is, where did the seed come from? And we have no idea. We have no idea. Literally, the seed is written, like it's stamped in the standard, and we have no clue where it comes from. Now, a couple of people have come forward and said they generated the seed, but we know nothing about how it was generated. And in fact, if I told you who these people were, you'd be a little worried.
Having a low Hamming weight for the P, doesn't this give us some assurance?
Oh, okay, so here's the problem. So first of all, the SHA-1 is supposed to kind of destroy any structure in the seed. The thing that we're worried about is, imagine there was like a discrete log algorithm for 1 out of 1,000,000 curves. So if all curves are dead, then fine, there's no security at all. If all curves are secure, then this is fine. The problem is, what happens if like only 1 out of 1,000,000 curves are insecure? In that case, you can pretty much see what the attack is, right? You loop 1,000,000 times until you find the seed that you can break, and then that's the thing you put in the standard. That's the concern. So yeah, so this is kind of the state of the world today. So yeah, there's this big transition to elliptic curves, but this is the curve that we all use. And the question is, how hard is CDH on this curve? And we have no idea. Yeah. So So in fact, yeah.
It sounds from what you said that 75% of the traffic today uses.
Yes, P256.
But that's not what happens. These websites support ECDH, but not most of the connections are not ECDH.
Most modern browsers support ECDH, and in fact use it by default. So in fact, there's a preference for forward secrecy, and there's if the browser supports ECDH, the server will choose it. And if you look.
So you have numbers for what percentage of connections.
No, those are hard. Those are difficult numbers to get. But we know that essentially Internet Explorer, Chrome, Safari, all the popular browsers, they all support elliptic curve Diffie-Hellman. And if it's presented as an option to the server will choose it. So that suggests that in fact the majority of connections to those websites actually do key exchange using ECDH. So very, very, very common. This one curve is being used everywhere. Yeah, if you're interested, in the paper we actually list, I said 96% use this, so you should ask what do the other 4% do? Yeah, so they do all sorts of crazy things. And in the paper we list kind of what they do.
Can the client ask for a different T?
No. The client says, I support elliptic curve Diffie-Hellman, and then the server says, I'm going to choose the cipher spec, and here's the curve you're going to use. Yeah, and it's named, P256 is one of the named curves, and that's how it's specified. Yeah, so good. So I wanted you just to be aware that this is happening, and in fact there's an active effort at NIST now to try and move to new types of elliptic curves. The focus seems to be mostly on performance. It's not so clear how you choose. There's really very little theory to tell us how to choose a curve that would actually give, that would kind of have some assurance that it's secure. So there's no family of hardest possible curves in the sense of random self-reductions. Yeah, so it kind of, it's not really this theory that's needed to help us in choosing these curves. Right now, that doesn't really exist. Okay, this was a quick, yeah.
Why not choosing a random curve?
Why not choose a random curve?
Why not choosing a random curve?
Oh, you mean every server would choose its own curve? Yeah, every server would just flip bits and choose its own curve. So it turns out that's actually not a good idea. And the reason is there are a lot of tests that you have. So we do know of many classes of weak curves. If you choose a random curve, there's a risk that you'll fall into one of those weak classes. So what NIST does is actually they hash, and then they check, is this one of the weak curves? If it is, they add one and they hash again. Is this a weak curve? So basically, P256 is the first curve which is known to not be, which is not subject to any of the known attacks that follows from the seed. So generating a curve by itself is actually quite a bit of work. Doing it correctly is difficult. So it's better that everybody uses a standard curve. Yeah, that's the reason. Yeah.
So do we know actually that you have for every large enough n more than many curves with the property that you need? So in other words, you know, like the number of the cardinal.
Yeah.
Do we know that?
Yeah, you're asking yeah. So it's actually most curves are fine. Most curves, in fact, have a hard discrete, as far as we know.
No. What I'm saying is you need more than that, right? In order to have the pairing, you need.
Pairing is a different story. Hold on. So far, these curves don't have pairings yet. Yeah, we'll get to pair. Now we're getting to pairings. Yeah, pairing curves actually. This is a really good point, actually. Pairing curves are very special. So in fact, these curves themselves don't have pairings. We're going to talk about pairing-friendly curves in just a second. What?
You really should not.
Well, it depends. I mean, it depends on what you want to do. If you want to use pairings, you should have pairings.
No, you're saying you use this for Diffie-Hellman key exchange, right?
No.
Well, no. Okay, hold that thought. It turns out it's actually not a problem. Yeah, pairings. If you know what you're doing, pairings are not necessarily a problem. In fact, the point of pairing-based crypto is that they're not a problem. They're actually a blessing. Yeah.
So using the same curve isn't that a bad thing in the sense of if in the future we have pre-computation attacks where
Yeah, excellent. That's an excellent question. So the question is, if we have pre-computation attacks, is it a problem that we use the same curve? So P256 is big enough that there are, doing pre-computation attacks is actually too difficult, as far as we know. Again, so the current methodology is. Look. This is I'm describing the state of the world. The state of affairs is everybody uses the same curve. That's the recommendation, and that's what websites do. And the question is, which curve should we use? So there's a need for more theory to decide to help choose curves. Okay, so let's go back to pairings. So that's kind of our topic. So as we said, basically some curves actually have additional structure called a pairing, and so let's define that. Now I imagine some of you have already seen this, so I'll kind of walk through this. Well, let's just walk through it. Okay, so what is a pairing? A pairing basically, abstractly, is something that operates on two groups. There's a source group, which we call G, and there's a target group, which we call GT. Now, normally the source group will be the points of an elliptic curve, and the target group will be just a finite field. Yeah, just elements in a finite field. And what a pairing does is it takes 2 points in the source group and maps them to the target group in such a way that the exponents multiply. Okay, so the pairing is bilinear, and bilinear here means multiplication of exponents. So formally what a pairing is a map that has this bilinearity property. So in some sense it breaks Diffie-Hellman because it allows us to multiply exponents in the exponent, but it moves us to a different group, so we can only do the pairing once and never again. And of course the requirement is that it's polynomial time computable, and it better not be degenerate, and it's not degenerate in the sense that it maps generators to generators. Okay, and as I said, the best examples we have so far is where the group G is a group of points of an elliptic curve, and the target group is basically a finite field, some finite field extension. All right, now why are pairings so useful in crypto? Really, there's two tricks that keep coming up again and again and again and again. Okay, so when you look at pairings, really one trick that we use all the time is that if you look at the pairing of g to the x and h to the y, you notice the x, y come out of the parentheses, and then they can go back into the parentheses in the reverse order. Yeah, so g to the x, h to the y is the same as g to the y, h to the x. So this we use all the time. That during encryption, say you use this, and during decryption you use that. So that's one reason why pairings are so useful in crypto. And the other reason why they're so useful is because basically they allow us to compute inner product on encrypted values. Yeah, so if you have a vector of exponents, a vector given to you in the exponent on the one hand and another vector given to you in the exponent on the other hand, you can compute the inner product of these vectors just by computing the product of the corresponding pairings. So these two tricks basically come up again and again and again and again and again in pairing-based crypto, and that's basically why we get the functionality that we get. More generally, you can imagine I might have a matrix here, so G to the power of some matrix and H to the power of some matrix. What the pairing allows us to do is compute the product of these matrices in the exponent. And we can only do a product of two matrices and no more. And that's, in some sense, the limitation of pairing. So we can multiply two matrices, and that's all we can do. Okay, so let's talk about some consequences of the pairing. Again, basically, if we have a pairing, then the decision Diffie-Hellman problem that we know and love in traditional group actually turns out to be easy. And here's how we do it. If I give you g to the x, g to the y, and g to the z, and you want to test whether z is equal to x times y, all we do is we just compute these two pairings. And by the property of the pairing, you know, the x and y comes out of the parentheses. You get equality only if z is equal to x times y. So DDH becomes an easy problem. So we can't do the standard Diffie-Hellman protocol in pairing groups. And the other property is we get this reduction from discrete log in G to discrete log in the target group. So it had better be the case that discrete log in the target group is hard. Otherwise, discrete log in the source group will not be hard. Okay, so those are the two immediate properties that we get out of pairings. And so now we can ask for like complexity assumptions that come up in the world of pairings. And basically, we get the standard complexity assumptions that we know and love. So we have discrete log is a perfectly, it's kind of a requirement for pairing-based groups. We need discrete log to be hard. We need the computational Diffie-Hellman problem. We'd like the computational Diffie-Hellman problem to be hard. When it comes to decision Diffie-Hellman, I already told you the decision Diffie-Hellman is not hard. That's an easy problem. But we can fix that basically if we just add one more element. You can see by magic of PowerPoint, you can see the elements that we add. And this becomes the new replacement for decision Diffie-Hellman. And a lot of encryption schemes actually use this as a randomizer for the encryption. And that's actually what we use for encryption and decryption. So these are just translations of the standard assumptions. So far, so good? Any questions so far? I guess so far we're just doing basic stuff. We'll get to more sophisticated things in a minute. Okay. So there's one assumption that turned out to be quite useful in the world of pairings. In fact, it's kind of almost like an assumption that allows us to build many different constructions. And that assumption is called a decision linear assumption. It's a little bit of a wacky assumption to describe. So I tried to kind of capture the cleanest form of it here. But again, this turns out to be the D-Lin assumption is almost the most important assumption, complexity assumption that's used in pairings. Many constructions that we'd like to have basically can be built out of this decision linear assumption. So let me try to explain it to you, and then we'll state a cleaner version of the assumption. Okay, so here we have it. So, all right, so I'm giving you a bunch of generators and a bunch of generators, k plus 1 generators. Now, what I do is I give you random exponents of these generators, and then I either give you the sum of these exponents, so a linear combination of these generators. That's where the name comes from. So either I give you a linear combination of these generators, or I give you just some other completely random exponent. Okay, the question is whether you can distinguish these two things. And if you can't distinguish them, then we say that the decision linear assumption holds. And again, as I said, this is a very important assumption in the world of pairings. Turns out there are many ways to argue that this assumption holds. You can give generic arguments, proofs to say that this holds. And as I said, many constructions reduce to this particular assumption. So if you like, this is like the LWE of pairings in some sense, some abstract sense. So in fact, so let me give you a little bit of intuition about the assumption in that there's this parameter k, right? It's called k decision linear. So it turns out the larger k is, the harder the problem becomes, right? So the harder the problem is, the weaker the assumption. So like 1 D-Lin is just GDH, which you can break using a pairing. 2 D-Lin, you can't break even if you have a pairing, but you can break if you have a 3 linear map. And similarly, and so on for k D-Lin. So we get a hierarchy of assumptions, and really this 2 D-Lin is a very crucial assumption that is very much useful in this world of pairing. Okay, so as I said, if you have a k plus 1 linear map, you can break k D-Lin. But if you only have a bilinear map, if you only have a bilinear map, a pairing, then all 2 D-Lin, 3 D-Lin, 4 D-Lin, all those seem to be fine assumptions to use. Yes?
Do you have a product in this exponent instead of a sum?
What?
So in the left distribution, the last term is g to the k plus 1 to the
Sum of the xi's, yeah.
It is sum.
It is sum, yeah, not product, sum. It's called a linear assumption because it's a linear combination of the xi's.
Well, in the DH you have g to the x, g to the y.
Well, let's wait. So if you plug in k equals 1, yeah, if you plug in k equals 1, you get g1 to the x1, g2 to the x2, versus g1,
G2 to the X1.
g2 to the x2. Oh, yeah. Sorry. Yes. Okay, ignore this. Right, you get g1 to the x1 versus g2 to the x1, or g1 to the x1 versus g2 to the y. That's exactly the DDH assumption. Yeah, so the multiplication is happening implicitly. But there is a multiplication going on there. Yeah, so this is DDH. Yeah, so it's a good question. So let me just tell you a quick variation. So there's a cleaner way of thinking of this assumption, which is kind of elegant, I think, kind of very clean, which is to say what the Delian assumption says is basically if I give you a random matrix under this assumption, decision linear, if I give you a random matrix in the exponent, so g to the different, I give you g to the first element, g to the second element, g to the third element, basically the entire matrix is given to you in the exponent, that's indistinguishable from g to the power of another matrix where the matrix is bounded by rank k. Okay, so that's a much cleaner version of the assumption, and typically when we use it, we actually use it in this form. Yeah, so basically what Delian, why it's useful, why decision linear assumption is useful, is it says you can't distinguish random matrices in the exponent from low rank matrices in the exponent. Okay, that's a cleaner way of stating the assumption, so we'll leave it at that. So far so good? All right. So what I wanted to do next, I need to speed up a little bit. What I wanted to do next, how much time do I have?
That's what I wanted to tell you. You said an hour, but it's an hour and a half.
Really?
Really?
Cool. Okay. So I can torture you. Well, you're after a deadline. I'll try not to go over too much, or maybe I'll leave time for questions and discussions. Yeah, okay. There are some things I want to get to. Okay, the next thing I want to do is tell you a little bit about where these pairings come from, and then we'll talk about applications. Yeah, so let's just go through this, and then we'll talk about applications. So where do these pairings come from? All right, so we have our basic elliptic curve group. So we have the group of points over a finite field. We're going to call this group G. So here I'm giving you pairings under the hood, how pairings actually work. Yeah, so there are Q points in this finite in this group. Q is the size of the group. It's defined over a field of size P, and we know that Q is about the size of P. Yeah, so far so good. Now, if we look at an extension, if we look at the number of points over an extension, so all of a sudden we look at the points on the curve, not just over FP, but in fact over FP to the alpha, over an extension to FP, what the image that pops up is all of a sudden there's another set of Q points, so that the so the group of order Q, the group of points of order Q is in fact a two-dimensional object. Okay, so elliptic curves naturally are you can think of them as two-dimensional objects. And again, basically you have a Q by Q, so ZQ by ZQ as groups of, as the points of order Q. Now you can take arbitrary 2 points in this two-dimensional structure, and it turns out on this two-dimensional structure there's this natural pairing that was defined by André Weil. So when Weil did his very, very famous work on curves, one of the things that he did is actually defined this pairing. I love this story, by the way. This is work that he published in 1949. Maybe some of you have heard me say this before, but André Weil actually defined the pairing while he was sitting in jail during World War II. It's really quite a remarkable story. So he wrote this autobiography, which actually is really fun to read. His autobiography is basically about his life during World War II and the utter chaos that Europe went through during World War II. And it's written from a perspective of a mathematician. What is it like to be a mathematician in time of war? And he actually refused to serve in the French army, so the French promptly stuck him in jail. And apparently he was for 2 years in jail or so. And he says this was apparently by law they're required to give him a pencil and paper. And apparently this was like the most productive time of his life.
So instead of giving us grant money, they should just put us in.
Listen, yeah. To the point, actually. So he says this in his book. He says in the autobiography he was actually considering sending mail to the head of the French Mathematics Academy to recommend that every mathematician spend at least 2 years in jail because it'll be so productive. Yeah, this is literally in his book. So yeah, so this work, defining this pairing, he did actually while he was sitting in jail. The odd thing to me is that he did extra work to make sure that his definition actually is computable. In fact, when you look at modern accounts of algebraic geometry, they give a very different definition of the Weil pairing, one for which it's easier to prove its properties, but it's completely useless from a computer science point of view. It's really odd that he did extra work just to get a definition that's computable. And so anyhow, so he gave a definition of a pairing, right? So takes this pair P and Q. The definition basically, all I did here is I just wrote it up very abstractly. What it does basically is there's this function f sub p, which is just a polynomial. Yeah, it's a polynomial in the coordinate. It's defined by the point P. There's a certain polynomial defined by the point P, and it's a polynomial. It's a bivariate polynomial whose inputs are the two coordinates of the point Q. Okay, so you take the point Q, you treat it as xy, and you just evaluate this polynomial, and then you do some cleanup at the end, and that gives you the pairing. That's it. So it's just a matter of polynomial evaluation. The problem with this polynomial is that it has exponential degree. And in fact, someone wrote a paper saying the pairing is non-computable because it has, this polynomial has an exponential degree. And what Victor Miller did in a seminal work in 1984 is he said, yes, this polynomial, this is a bivariate polynomial. It has exponential degree, but in fact, it has a short straight line program which allows us to evaluate it very quickly. Now, interestingly, Victor sent his paper to Stock. It was rejected from Stock because it had no applications. That was the reason. And he had never published it. He had actually buried it for ages. I like this example of if any you've just sent your papers to TCC. So if you get back comments that the paper has no applications, like maybe what happened recently, then you can always refer and commiserate with Victor Miller and make fun of the committee many years after the fact. Yes? So anyhow, this finally was published in 2004. It was kind of too embarrassing that such an important paper would remain unpublished. So finally this was published in a 2004 special issue of the Journal of Crypto. Yeah, so anyhow, so he showed that in fact the pairing is computable and it has all the bilinearity properties that we would want. There's only one problem. Yeah, there's only one problem, which is what we would like to have is just, we don't like to think in crypto, we don't like these two-dimensional structures, right? We always think in terms of cyclic groups, not two-dimensional structures. So we'd like to basically have our pairing just defined on this ground field, on this ground group. The problem is that if you take 2 points in the ground group, so if P and Q live over here, their pairing would always be 1. So it's degenerate on this ground field. So that kind of is unfortunate. But now there are many ways to fix it. And so one way to fix it is you can use particular sets of curves on which there is what's called an automorphism map that basically allows you to move the point. So when you want to compute the pairing of P and Q, you first move the point. Yeah, you move it to somewhere outside of the ground field, and then you're guaranteed that it's non-degenerate. So you actually define the pairing as P plus this automorphism of Q. And that gives you a symmetric pairing. Yeah, so both groups are the same, mapping you to the target group. So that's one type of pairing. And the other type of pairing is what we call an asymmetric pairing, where you actually have two groups. You have a group G1, and then you have a group G2 defined over this extension field. Again, this group has to be chosen somewhat carefully. And again, you would get a non-degenerate pairing on these two groups. Now, the interesting thing is, in this setting, if you just look at the group G1, there is no pairing on it because the pairing is degenerate. If you just look at the group G2, there is no pairing on it because the pairing is degenerate. So in fact, you're in this funny situation where you have a pairing defined on G1 cross G2, but since you have no pairing on G1 and G2, DDH actually appears to be hard both on G1 and on G2. So this is sometimes called a symmetric XDH assumption, that we have a pairing, but even though we have a pairing, normally pairings break DDH. In this settings, actually not only do pairings not break DDH, we actually have two groups where DDH is believed to be hard, and this actually has a whole bunch of applications just on its own. Okay. Yeah, so that's asymmetric pairings, and it turns out this is actually the way to implement it. When you implement pairings in practice, you always implement them using these kind of groups. Yeah?
Two questions for you.
Yes, please.
Previous slide.
Oh, previous slides. Okay,
So
yes.
first of all, even one
Oh,
earlier.
even one before that.
Yeah, sorry. So
This
first of
one.
all, why is it that you said this is Tate pairing when
Yeah.
you said it was due to Vey?
Oh, excellent question.
And
Yes,
then
yes.
My second question is, if Miller's paper wasn't officially published until 2004, how did it get disseminated? So
Oh, yes, yes, yes. You know, this is the beauty of the internet. So, yeah, he wrote his paper in '84.
the internet. That's
Well, the internet was around in 1984. You know, I was barely born then, but it was around. So
But already attended crypto.
84. Ah, that's right. There you go. Yes. I think I was in 6th grade back then, or 5th grade. I don't remember exactly. Anyhow, so the first question is, why is it called a Tate pairing? Well, okay, so the Vey pairing actually is defined slightly differently. It's actually defined as a ratio between two functions. It turns out the denominator, well, force basically slows you down by a factor of 2. And what was observed is, in fact, that even if you get rid of the denominator and you do this extra cleanup step, then you can get rid of the denominator. So everything works twice as fast, so you might as well just use this. So the reason it's called Tate pairing is basically half of the Weil pairing. That's all that is. And how did Victor's paper get disseminated? That's actually a good question. Oh, yeah, I know how it got disseminated. So what happened is, so Victor wrote his paper, and it was unfortunately rejected. But then he circulated it among, friends. And Menezes, Okamoto, and Vanstone learned about the pairing and the fact that it's computable. And they came up with this reduction from discrete log on the elliptic curve to discrete log on the finite field using the pairing. And that's where they attribute, of course, the algorithm to Victor Miller, and that's exactly where that's how it became well known. Yeah. So if you have a result that's not published, get somebody else to write a strong paper that uses it.
It also helps that he worked for IBM Research. So.
Yeah, it was disseminated inside of IBM. Yeah, that's true. That's true. Very, very, very true. But also there was the internet. Yes, Trika.
Isn't there the obvious application for breaking DDH on certain class of elliptic curve groups? I mean,
yeah, back in 1980, this is pre-DDH. DDH, actually, the first paper I know that uses DDH is from 1991.
But there's the Diffie-Hellman key exchange protocol, right? And if you use elliptic curves, then at least it allows you to distinguish which is not exactly,
Yeah, that was noticed much, much, much later. That was noticed in like 2001. Yeah, but yeah. So you're saying, but it actually allows you to somewhat weaken discrete log. That was kind of what they were excited about. The DDH aspect of it was noticed much, 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 much later. Yeah.
So if you want to pick you want to have one that has a prime number of points on it, right?
Yeah.
So how do you?
Oh boy. Okay. Okay. That's an excellent question. Yeah. So that's actually an excellent question. There's actually a whole field. In fact, there's a whole conference devoted to how do you pick pairing-friendly curves where the number of points is prime. Yeah, this is not a question I want to answer here. I'll say that in this first case.
My question is, can you even do it for every n?
Yeah, you can. Oh.
How many are there?
No, you can do it. Okay, so under appropriate assumptions about densities of primes, you can do it for every n. Yeah. Yeah, you have to assume primes of special form. That if I give you a polynomial, then the density of primes along those polynomials are dense enough. It's true, but proving these things is always kind of tricky. So under appropriate assumptions on densities of primes, this will exist for every n. Yeah, I guess that's what you were asking.
Yeah. And also then when you map over to the target group,
Yeah.
you need to have the same number.
Yes.
Of elements.
That's right. So you basically have when you construct pairing-friendly curves, basically you have two parameters you want prime. You want the size of the source group to be prime, and then you want the size of the target group to be divisible, or the finite field needs to be the finite field minus 1 needs to be divisible by the size of the source group.
So my question is, so your curve has that property.
Yes.
How many curves is there?
Yeah, so it looks like using this method, you can basically.
So it's that curve.
This particular curve, anytime p is 3 mod 4, you'll have a pairing group of size p plus 1.
So it's not a general curve, it's that curve.
It's that curve. This is one method. The second method, actually, this is where the more complex, this method actually will also let you build curves of arbitrary size, but here this is harder. This actually takes more work. But once you find the curve, everybody can use it, much like we did with P256. Yeah? Does that answer the question? Okay, cool. Yeah?
How big should we think of alpha here?
Yeah, so the alphas are very small. So alpha, you don't want it to be too large because the larger alpha is the slower the operation. So typically you would think of alpha as like 6 or 8 or 10 or 12. That's as high as it goes. Yeah? So this P would be like 256 bits. And then you want alpha to be, you know, like 10 so that the resulting finite field is 2,000 bits big so that discrete log on the finite field is hard.
Do we know that for a given value of alpha that there exists an infinite family?
No. Actually, the constructions are for specific alpha. And in fact, you don't want alpha to get too large.
Right, no, but for a fixed alpha, let's say alpha equals 8, do we know that?
Well, if you say alpha equals 10, then yes, there's a family that will give us as many curves as we want for varying sizes.
For alpha equals 10.
For alpha equals 10, for alpha equals 12, yeah, for those kind of alphas.
For an infinite sequence of alphas?
Well, so there's a paper, there's a taxonomy that actually goes and analyzes many different alphas, like I think up to like alpha 100 or so. And for each one, they say here's the best family to use.
But what about for an infinite sequence of alphas?
Well, you don't want alpha to get too large because if alpha is...
As p grows, there's some relationship, right? Isn't that true?
Yeah, so no. I mean, this goes beyond the... So alpha of 100 is beyond what people were interested in. So I'm sure it's doable, it's just no one bothered to do it.
But theoretically, as you move p to infinity, then you do actually want alpha to eventually...
To grow as well, yes.
Grow, right?
That's right.
But that's not understood.
It's just because no one wrote it down, but it's not that difficult to actually do. Yeah, it's a good question. Great. Any other questions? Okay. All right. So far, so good. So let's move on to more interesting things. So that's where pairings come from. So the first question you want to ask is, well, can we generalize this? So as you know, pairings are only the beginning. Kind of the real magic comes from multilinear maps, right? So not just two linear, but multilinear. So the question is, can we generalize these constructions to actually build multilinear maps? And the first goal, the easy goal, would be, can we just have a three-way multilinear map, right? So we want to take 3 copies of G and map to GT such that we have a three-way multilinearity. Yeah, that's the three-way multilinearity property. So I didn't want to write this down in the slide, but I'll just tell you in 1 second that really the standard Weyl pairing, you can actually think of it as a determinant, a 2x2 determinant. If you visualize things properly, literally what it's computing for you is a determinant, 2x2 determinant, and that's why it's bilinear from the 2x2 determinant. You can generalize that and ask, well, what if we just define a 3x3 determinant in exactly the same way? Yeah, so you can write down very precise definition of a 3 multilinear map, and in fact it will be multilinear, and it's like the dream come true. Unfortunately, we showed, this is in work with Alice Silverberg, that in fact all these natural generalizations of pairings from algebraic geometry, so generally on abelian varieties, none of them, even though they're all multilinear and they have all the properties, hard discrete log, multilinear, everything we want, unfortunately none of them are computed by polynomials in the way that the Weyl pairing is computed by polynomials. And there's a particular way you show that it's not computed by polynomials. Basically, you show one Galois map that kind of this thing is not invariant under. And so there's something magic about the number 2 that makes the pairing computable. The minute you go to more than 2, it's no longer computable. So if we want multilinear maps, which we definitely want multilinear maps, if we're going to build them from algebraic geometry, we're going to have to come up with a completely different way of doing it. So, of course, my favorite result of the last decade, huge results, is a multilinear map. I don't, you guys have heard about this to infinity. Of course, Gard, Gentry, and Halevi came up with this beautiful result, but it doesn't quite solve the original problem in the sense that the multilinear map operates on noisy representation of group elements and not actually kind of these clean algebraic representation of group elements. So a major open problem, this is actually where I'm spending a lot of my time these days, is basically kind of looking at other types of pairings that would come more from traditional algebraic geometry and see if there's a way to generalize them to get a 3 linear map. I am absolutely convinced this exists. Like if I went to sleep now and woke up in 100 years, I am certain that we will have a clean 3-way multilinear maps without noise. I'm absolutely convinced this exists. but everything I've tried so far doesn't work. So, please think about this too.
Do you think it'll naturally also give a graded algebra?
What?
A graded algebra? Like you have to...
Everything we look at actually is a graded algebra as well. It's not just a pairing. The problem is, what happens is always one of two things. Either we get a wonderful multilinear map that's not computable, or we get a wonderful multilinear map that's computable, but discrete log is easy. Yeah, we somehow always get stuck with one of these two things. But I'm convinced this exists, and so we'll see.
How many years in jail you need?
I think this is a good measure of hardness. How many jail years? Yeah.
But Dad,
Yes.
people are offering money to solve the problems
Oh.
here, and we have a board upstairs.
Ooh, I
so
see.
how much are you putting on it?
What's the highest prize right now?
What's the highest?
$3.
No. There's at least there could be a 200.
A few million.
There's a 300. There's a 300.
Did you say 3 million?
Few million FHE, which is as efficient as factoring, Google price.
No, but we're
I
in
see.
the small hundreds.
Small hundreds. I would.
What are you putting on?
5 months in prison.
So what are you putting on? So what are you putting on?
I'll wager. I'll be your friend forever. A, and B, I will definitely do hundreds. Even 1,000. You know what? 1,000. I will do it. Okay. So you caught me in a generous mood. Yes. Please work on this. Okay. So, yes. Question.
I was curious about you. It says non-computable bipolynomials. Can you talk about what the bipolynomials part of that? Why do we need bipolynomials?
Yeah. No. Look, it's impossible to prove that things are not computable, right? So what we would try to do is naturally generalize the algorithm that Miller gave. The algorithm that Miller gave basically defines a polynomial. The polynomial, based on the point P, defines a polynomial. And the polynomial evaluates at the point Q to give the result of the pairing. So what you would like to do is basically think of a polynomial that would take the coordinates of these three inputs. So it would take 6 inputs and produce the pairing as a polynomial, because that's how the Miller's algorithm works. Even though it's exponential degree, it's still a polynomial. So what you can show is that's not possible. Yeah, it's not going to be a polynomial, and you do that by using Galois maps. It doesn't mean that there might be other ways to compute it, but that would take us, again, that would require a completely new idea, and we're not there yet. Yeah.
You're convinced it exists, but you're also convinced that something is hard about it?
Yeah. When I say exists, I mean it's computable, and B, has a hard discrete log problem.
So you can only, at the end, something confuses me.
Well, here, look. Here, the challenge problem is just this. Basically, I want a 3-way map where discrete log in GT is hard. So E should be computable, and GT should have a hard discrete log.
Okay, so and we don't need a zero test because there's no noise, or what's
Yeah, we don't need a zero test because there's no noise. I mean, so zero tests are needed because you can't compare things because of the noise. If you don't have any noise, the way you compare things is you just compare them as bit strings. So you don't need a zero test at all. You can, in fact, do a comparison at any level, not just at the top level. Unique representations, exactly. So it's a unique representation of group elements. So every group element has exactly one representation, a canonical representation.
Intermediate ones you can't compute. I mean, you can compute.
You can compute.
So you can go, okay, something's got to be hard in the middle. Not graded, right? Oh, okay.
Yeah, so this was a simple multivariate map, but you can talk about the graded version of this, where you would go from G times G to G1, and then from G times G1 to GT. Yeah, and in fact, all the construction we look at, they always have this grading property. But the point is exactly, you want to have every group element should have a unique representation. And that would allow us to get rid of noise, so that presumably when we do obfuscation, when we do a very, very high degree of multilinearity, the noise isn't going to blow up because there is no noise. So there's hope that this would give a much more efficient way to obfuscate. That's the hope. Whether it's true or not, some of us have to go to jail for that. Yeah.
If you have multilinear map for large N, right?
Yeah.
It's necessarily insecure, like your result with Lipton, right?
It depends on the degree. Yeah. So it depends on how multilinear. Yeah. So if you get to exponential multilinearity, you have problems. That's true.
So
yeah.
Necessarily, sort of, is there a?
Yeah. That's why I'm very modest. I'm only asking for a 3-way multilinear map. Yeah. Just let's start small. So 3, not 4. Yeah. So the feeling is the way the constructions would always work is you would specify k, and then we would come up with the algebraic structure that supports k but not k plus 1. Now remember, k is going to also derive the prime. So if your k is too big, the prime is going to be even bigger. So you'll never reach the black box results. Yeah, that's how this will play out. Cool. That's a really good question. Yeah.
So implicitly, you're also asking that there shouldn't be an efficiently computable map in the reverse direction.
Oh my God! Yeah. Okay. So yes. So what Amit said is exactly right. So if we had a bilinear map, if we had a bilinear map that went from G cross G to G, yes, that would be remarkable. Where discrete log is hard. Well, first of all, there would immediately be a sub-exponential attack on discrete log, but it wouldn't be broken. So that is possible, G cross G to G, and that would essentially give us, what was the $3 million prize? That would give us fully homomorphic encryption that's really cheap, because you can just keep computing on the same group and never change group, and you can compute for as long as you want. Yeah, so that would be remarkable, but that I mean, even in 100 years, I'm not sure that I don't know if it exists. Yeah, so that's probably too hard. Was that clear? If you have,
Just an algebra.
what?
It just becomes an algebra, no?
It becomes an algebra. That's right. That's exactly right. Yeah, with a hard discrete log. So we're nowhere near anything like that.
How would they make it semantically secure? Is it all
Yeah, you would have to randomize, right? So you would do El Gamal on top of that, and I mean that we already know how to do. Probably you would, and yeah, we know semantic security is the easy part here. Okay, cool. This is a really good discussion. So please solve. Work on this problem. I think it's really interesting and would have a lot of consequences. Okay, so before we move on to application, I just want to acknowledge early work on pairing-based crypto. So of course, I already told you about Miller's seminal work. Menezes, Okamoto, and Vanstone, kind of the first application in terms of attacks. Zhu came up with the first positive applications of pairings. There's an interesting story here that Antoine tells me that what he did is basically he came up with an implementation of the pairing for the purpose of implementing this attack. The problem is, so he came up with the best implementation up until that point took a couple of minutes to run. And Zhu came up with an implementation that runs, blindingly fast. And he tried to publish his paper, and it kept getting rejected again and again and again because people said, it's an attack. Why do we care if it runs in minutes or seconds? It doesn't matter. It's an attack. And attacking something in minutes is just as good as in seconds. And so he said, fine, here's a positive application just so that he could get his paper published. Yep. So sometimes the fact that committees reject your paper is actually inspiring new research. And then, of course, there's a team in Japan, Sakai, Gishi, and Kasuhara, who also did very nice early work on pairings. And then, of course, the work with Matt and so on. Okay, so, and of course, many others since. All right, so now I want to switch gears. Oh my God, I don't have a lot of time.
Half an hour.
Half an hour, I see. Okay. All right, well, I guess I'll stop when we all get tired. Or hopefully before. All right, so let's talk about some applications. So pairings basically, well, as you know, thanks to all of and many of you, pairings are kind of everywhere. I started actually writing out all sorts of the citations to all the papers, and there's just no way to fit it all on a slide. So when I say many contributors, that's everybody in this room and others. So of course, pairings give us new forms of encryption, identity-based encryption. I'm not going to define what attribute-reduced encryption, predicate encryption, somewhat homomorphic encryption. Tal mentioned that at the beginning. This is encryption that allows us to do one multiplication and no more. It allows us to do broadcast encryption, where the broadcast ciphertext is constant size, independent of the size of the set you're broadcasting to. Searchable encryption, we get new signature schemes, we get new NISICs, thanks to Amit. We get new SNARGs, thanks to Ale and others. We get new accumulators, thanks to Anna. Adaptable previous transfers. This is a beautiful result to Susan. We get PRFs. Where's Yevgeny? We get PRFs, VRFs, anonymous credential systems, anonymous digital cache, and many others. So basically, pairings have been, as you know, extremely productive in crypto. I guess what I wanted to say is, first of all, this is what we could do with a two-way linear map. Oddly, a three-way linear map doesn't seem to help us much. Yeah, we don't, like, even though we don't know how to construct them and it's a good goal, a three-way linear map by itself doesn't seem that useful. It goes, no-way linear map gives us Diffie-Hellman, two-way linear map gives us IBE and all this other stuff. Three-way linear map doesn't give us much, but many-way linear map gives us the magic of obfuscation. And so when you go to a many-way linear map, all of a sudden all these things become better. So attribute-based encryption becomes for circuits, not just for formulas. Predicate encryption becomes way, way stronger. You can get functional encryption. Of course, we get K-way homomorphic encryption, and we get even better broadcast encryption. Now, I just want to say in words what happens when you apply this to what happens to this box here when you use LWE. So it's quite interesting. So LW is a fantastic, fantastic assumption, extremely productive as well. I love lattices. I love learning with errors. So thanks, Chris, and many others, and Vinod. I mean, wonderful, wonderful results there. And so in the world of LWE, again, attribute-based encryption becomes applicable to circuits, and even in stronger ways than we can do with multilinear maps. Predicate encryption, I guess, there's progress, but we're not quite there yet. Of course, the killer app for LWE is fully homomorphic encryption. This is way better with LWE than with pairings. The one interesting thing is broadcast encryption. So this I would like people to encourage folks to work on this. So with pairings, we can get broadcast encryption where the size of the broadcast ciphertext is always constant size. It's quite remarkable. You can broadcast to a large set of people, and it doesn't matter how many people you have, the broadcast is always constant size. Oddly, with LWE, we still don't know how to do this. Now, we have good candidates for doing it, but we can't prove that they're secure from LWE. It's a little bit frustrating in that we can't break our candidates, but we can't prove security from LWE. So if anyone is interested in thinking about broadcast encryption, I'd be happy, very thrilled to send you our proposed construction.
Maybe we should just make up more variants of LWE like we do in the case of bilinear.
Yeah, so the funny thing is with a variant of LWE, we do know how to prove security, yes, but that's not the LWE game. In the world of lattices, you're supposed to prove things from LWE. Would you agree, or? What? I don't know, that's a rule I would like to follow. It'd be nice to have just one assumption from which everything follows. That's also why I kind of mentioned the decision linear assumption, because it's one assumption from which everything else follows. So yeah, if we start making changes to LWE, I mean, it's a little disconcerting, because if you start making changes, often the constructions break, the assumptions break. So anyhow, so if anyone is interested in broadcast encryption from LWE, I would love to send you some proposed candidates. See if you can break them or maybe prove security. That would be really nice. But it is a bit of a gap here. Again, we can do this with pairings. We can't do this with LWE, and it's probably because, I don't know, no one has figured it out yet, but it's probably doable. Okay, so now that we kind of have this list, I can't talk about all of these applications. I figured I'll talk about just one application that I like, and let me talk about the application of pairing to signatures, and then we'll stop. Question?
Either way.
Yeah, please.
So you mentioned obfuscation as an application of multilinear maps.
Yes.
So exactly what assumption do you need?
Oh my God. Really? Horrible assumption. I mean, it's a.
Subgroup elimination assumption.
Well, it has a name, yeah. It's a well, you know, it's an, what can I say? Yeah, it's a complex assumption on multilinear maps that's needed for obfuscation. But you know, hopefully this will get better over time. Again, there's constant improvements in obfuscation constructions. Hopefully the assumptions will get better over time.
I think it's a very constant improvement.
Well, you know, it's an assumption. We can write it down, you know, so it's already better than what we had initially. Thanks to the obfuscation team. Yeah, so that's where we are. Yes, exactly. Okay, so let's talk about applications of pairings to signatures. And I just want to kind of walk through one particular signature scheme and talk a little bit about its properties. And then I guess we'll conclude. So this is the simplest applications of pairing. So if you haven't seen pairings before, this is the easiest way to explain why pairings are useful. So I hope this will be interesting to those of you who have not seen pairings before. So these are called BLS signatures. And so this is a signature scheme that works as follows. So we have our two groups, so G1 and G2. I'm using the asymmetric settings here. The secret key is really simple. The public key and the secret key is really simple. The secret key is just some number alpha in the range 0 to q minus 1. And the public key is just g to the alpha. So what could be easier than that? Alpha, the base of the exponent is the secret key, and g to the alpha is the public key. The way we sign, again, really simple. All we do is we take our message, we hash it to a point in the base group here, and then we just raise the result to the alpha. What could be simpler, right? Hash and raise to the alpha. And that's your signature. The question, of course, is how do you verify a signature? And the way you verify signatures is, again, very, very simple. It basically requires two pairing operations. So you pair the signature with one generator, and you pair the hash of the message using the public key, and you verify that the two are equal. And just a bit of thought shows you that, in fact, if the signature is valid, you can see the signature is h of m to the alpha, and the public key is g to the alpha. So the alpha comes out of both sides, and in both cases you get something that's equal to this quantity here. So if the signature is valid, you'll get equality. If the signature is invalid, you'll get an inequality. That's it. That's the whole signature scheme. Really, really, really simple signature scheme. And you can prove... Yes?
What do you need G1 for?
What?
G1. What do you need G1?
Well, I explained this is the asymmetric version of BLS signature. So G1 is the group of points over the base field, and G2 is the group of points over the extension field.
No, the question is G1 is not used anywhere.
That's the target of the hash function.
Yeah.
Maps to G1.
Well, no, I see what you're saying. Fine. Actually, it's used in the hash function, but implicitly. So we'll leave it in there for completeness. And then you can prove a theorem basically that says that under kind of what we call the asymmetric computational Diffie-Hellman assumption, this just comes up because we're using asymmetric pairings, then in fact the signature is existentially unforgeable in the random oracle model. So you need this hash function to be a random oracle, and then you can argue that this is secure under CDH. So it's a really, really simple, it's the easiest way that I know to explain the benefits of pairings. And the only thing is, of course, this is a signature scheme that can only be analyzed in the random oracle model. So what I want to do very quickly is talk about three properties of the signature scheme. I think it's three properties that have kind of not been utilized practically as much as they should, and so I just want to kind of point them out. The first property is that the signature is really short, and there's a beautiful open problem here that I want to mention. So if you think about what a signature here is, a signature literally is just one group element in the group G1. That's it. Just one group element. So a group element in principle can be quite short, and here I wrote down the signature sizes. So let me back up 1 second. So what we'd like to do is we'd like to have short signatures. Short signatures come up in a variety of contexts. For example, at some point, I got an email from the South African DMV where they were worried about car theft, and they decided to print signatures on all their license plates. That's why there's a license plate up there. And they tried various signatures, and there was literally just no space for the barcode on the license plates, so they Googled short signatures, landed on my page, and sent me an email saying, can we use your signature scheme? So I said, great, it's not patented. Actually, funny story about patents there, but it's not patented. Yes, it's open for anyone to use. And so that's one case where you have no space, so you want a short signature. Another case where you want short signatures is where a human has to type in the signature. There are situations where a human needs to type in a signature. Very often, in the case of digital rights management systems, the secret code that you type in to activate something, very often that's a digital signature, and there it's very important that the signature is as short as possible. So the question is, how do we build short signatures? And the particular problem is, suppose you want a signature where the best known attack runs in time 2 to the lambda. What's the shortest possible signature we can have? Okay? So you want best attack to run in time 2 to the 128. What's the shortest signature we can have? And here I wrote down the signature size for the different schemes. And you can see, using the pairings, because we only have one group element, the signature size is only 2 lambda. So 256 bits. Why is it 2 lambda? Does anybody know why is it not lambda? Why is it 2 lambda?
The attack takes square root attack.
Square root attack on discrete log. Yeah. So in a group, you want discrete log in the group G. You want CDH in the group G to be hard. So there's always a square root attack on discrete log, and so we have to double the size of the group to get security, to get the best attack to run in time to lambda, and that forces us to use 256 bits. So so one property is that it is very short, but there's a beautiful open problem here, which is why are we stuck at 2 lambda? Why can't we beat this 2 lambda bound? And this has been driving me nuts actually for a long time. Like, why can't we come up with a lambda bit signature where the best attack runs in time 2 to the lambda? And again, there's beautiful, beautiful work by Sahai and Waters that shows that using obfuscation, in fact, you can get a lambda bit signature. I'll tell you, the signature is really simple. Basically, it's a MAC. Yeah, well, it's a puncturable MAC. But basically, the way you sign is you compute a MAC of the message, and the way you verify is you publish a public key, which is an obfuscation of the MAC verification algorithm. So the signature is always lambda bits and has security 2 to the lambda. Of course, with the current state of obfuscation, the South African government would have a little bit of trouble implementing this. Yes, it would take a while. I mean, car thieves would get away with a car before they can verify the signatures. I think the car would be obsolete by the time they can verify the signatures. So the open problem, again, I would encourage, I really hope someone can solve this problem, is basically, can we have an implementable method? For example, can we use a lambda-way multilinear map, right? So a 128-way multilinear map to get a lambda bit signature.
But then, I mean, if you do just a birthday attack on the hash function, you already need...
Oh, I didn't say it has to be a hash and sign. Could be any.
But if you want to assign arbitrary bits...
Look, we have an existence proof. We have an existence proof.
Right, I know, but it's for a fixed message space. If you want to sign up, arbitrary messages, you're going to need to hash.
Yeah, but it doesn't mean that the output of the hash is the size of the signature, right? You could hash, and then the signature could be even shorter.
Hannah is thinking of using the signatures as a hash function. You can give a reduction showing how to build hash functions out of signatures. Is this what you're...
No, but that's interesting.
Signatures can be based on one-way functions, right?
Right. Well, those are not short, but yeah, in principle, you don't need hashing for signatures. Yeah. So yeah, the fact that the fact that a hash has to be size 2 lambda is not necessarily an impediment. So yeah, so we know that this is possible, and we'd like to do it in a better way. LWE, it would be interesting if LWE can do something like this, although LWE signatures don't seem to be in this table anywhere, but again, maybe over time, this again, a wonderful question. Could we build short signatures using LWE? Yeah, that would be really nice.
But then when you say it's possible with lambda bits, I assume you mean if you assume I/O with some completely insane security assumption, like that the only...
Well, you assume I/O. All you need is I/O.
No, well, I mean, with lambda bits, if lambda is secure, you need the best attack is 2 to the lambda. For what assumption? Short. Is that like
an appropriate assumption on the I/O scheme? Oh, I see what you're saying. So remember how the signature scheme. Remember how the signature works. The signature works. The signature basically is a PRF of the message.
Right.
So as long as your PRF has security 2 to the lambda, which is fine, then the signature will have security 2 to the lambda.
You publish the public key, so presumably...
The public key is an obfuscation of the PRF. So that security is kind of independent of the security of the signature scheme.
I see, so you can make it huge, I see.
You can make it huge. By the way, I'm surprised nobody complained. The proof here is only selective security, but we don't care about that because you can do complexity leveraging that only impacts the size of the public key, not the size of the signature. So in fact, might as well assume this is a fully secure scheme. Yeah?
Can you always go to lower lambdas as well?
Lower lambdas?
Even shorter than 15.
Oh, below lambda bits?
Yeah.
No.
But I mean, lambda being lower than 56 bit. So there's no limitation. I mean, do things break down if you make things smaller?
Oh, what I'm saying is anything below 2 lambda. I'll take even 1.999 lambda. Yeah, that would be pretty cool too. 1.5 lambda. That would be pretty cool.
Yeah, no, I think I'm asking a different question.
Yeah.
Some applications you may not want 120 bit security. I'm saying, can you...
Oh, yes, yeah, I see what you're saying. Yeah, you can always, I mean, if you want lambda equals 64, then this would be 128 bits.
So nothing goes wrong if you...
Nothing, well, except that you have an attack that runs in time 2 to the 64. Yeah, but everything scales down if you want to. But at some point, the scheme stops being secure if you scale it down too far. So again, this is a really beautiful problem. I hope no money here. But maybe you'll get money from the South African government. But this is a beautiful problem to solve. All right, and the second property, and then I think I'll stop. The second property is it has not only are the signatures short, but it turns out you can take a whole bunch of signatures and compress them into one. This is a paper with Craig and Lin and Shaham that basically shows that you can take a whole bunch of signatures produced by different people and compress them all into one signature, and this one signature in fact convinces the verifier that in fact user I, for all I, user I really did sign message number I. So not only are they short to begin with, you can compress them all into the size of a single signature. And let's show you one example where this comes up. If you think of certificate chains, so imagine somebody gives you a certificate chain where the signatures in the chain are all these BLS signatures. So today, these signatures, you have to list all of these signatures in the chain. Using aggregation, you can compress all of those into a single signature and shrink your certificate chain. So this would actually reduce traffic in SSL, but this is not used today, unfortunately. What?
Why?
I don't know.
How about computational? They are short. How about computation?
So verifying them takes just a few milliseconds. So that's fine. And the verification is done on the client, so a few milliseconds on the client is fine. Yeah, so why they're not used, I don't know. I mean, this is really kind of a shame. The world would be, a better place, but it's not used. And also, similarly, by the way, in Bitcoin, for example, today the way Bitcoin works is they generate a bunch of transactions, and then those transactions become a block. Then they generate more transactions, and those transactions become a block. Today, all the signatures in the transactions have to be recorded because that's how money is transferred. You could reduce the size of the blockchain, at least the transactions on the blockchain, by, again, aggregating all the signatures in the block into a single signature. Not used today. Why is it not used? I think people are not aware that this property exists.
But you need like hashing into the elliptic curve groups and all these kind of things.
Yeah, but that's quite easy. Yeah, that's not a problem. Yeah. Okay, so I'll just say quickly, how do you aggregate? Well, the way you aggregate is really simple. You just take all the signatures and just multiply them together. And it turns out, I'll skip this if you do the math, it turns out you can verify the aggregate and everything just works. And the last property I'll mention is that in fact, it's very easy to thresholdize these signatures. If you think for 1 second about how the signature works, it's just raising something to the power of alpha. So making it into a threshold signature is trivial, and similarly, distributed key generation is trivial. There's really nothing to do. So it's like both signature generation and key generation are very easy to distribute. Whereas in RSA, you remember, it's easy to thresholdize RSA, but it's kind of difficult to generate the key in a distributed manner. Schnorr and DSA have kind of the opposite properties, where here both sides are easy. And again, I'll mention another open problem that I really like. For some reason, I don't know why, from LWE, it's still really hard to get threshold signatures. Yes, so again, for folks working on LWE, this would be a really nice thing it's kind of missing in the world of LWE. We'd like to get threshold signatures for large number of participants and large thresholds, and somehow when when we do threshold signatures, basically we multiply partial signatures by binomial coefficients to do the interpolation, and this multiplication by binomial coefficients tends to blow up the noise. And so it kind of ruins what we can get from LWE. So Chris actually has a wonderful paper starting to build LWE-based threshold signatures. But again, it's fairly complicated threshold schemes. It's nowhere near as simple as RSA or BLS. And it's kind of this problem, again, kind of drives me nuts. It would be really nice if we had an LWE scheme where the threshold property is literally as simple as RSA or BLS. Today, we don't know how to do it. So, LWE is a wonderful, wonderful assumption and a beautiful thing to work with. But oddly, there are still basic things that we want to have that we can't build from it.
How do you define simple? I mean, how are we going to judge?
No, simple is very, very precise. So what I mean by simple, I'll just say it in one word. Simple just means that the signer sends the message to a bunch of servers. Each server computes the signature on its own, no communication between the servers, sends the response back, and then if enough servers respond, you can combine them to get the signature. That's simple. That's it. And we don't know how to do that with LWE today. Yeah. And again, I think that's a gap in our LWE understanding, and hopefully it will be resolved. I think what we need is basically a new LWE signature So the existing signatures just don't have this property. We need to invent a new type of LWE signature such that it would have the threshold property.
So then how practical existing LWE signatures non-threshold? Are they actually practical? Like encryption is practical. I mean, somewhat practical. If you
Yeah.
So signatures are practical based on LWE?
Non-threshold signatures?
Non-threshold, yeah.
Very practical, yeah. Well, they're long, but they're very practical, yeah, of course. Absolutely. But when it comes to threshold, and by the way, these thresholds, I mean, thresholds are just the world needs. I mean, when you look at certificate authorities always store their keys in a threshold manner. So you can't use LWE signatures until we come up with a threshold mechanism. So it is kind of important. Yeah?
Your question about lambda-based signatures, is it open in the random oracle model?
Is it? Oh, no, we don't even know how to, even with random oracles, we don't know how to do it. The only assumption that seems to help is I/O. There's actually, when we try to construct it, it looks like every construction we consider, it looks like to get security or to actually consider the construction, we almost need obfuscation to make it work. So there might even be, maybe there's some impossibility result that...
How about the one-time signatures? One-time signatures.
I don't know. It's an excellent question. Yeah, I don't know.
It's open even for one.
Yeah. That's an excellent question.
No, one-time signature.
Short one-time signatures?
For a single bit, let's say.
You have to give a full preimage. Oh, I see. For single bit, it's easy. Yeah, but for many bits? Yeah. I don't know.
Minimal description of the question. How long is your message? Is it?
Say it's basically 2 lambda bits. Say so. It's the output of a hash function. Yeah, that's it. Yeah. That would be really nice. Actually, I think there might even be some lower bounds on the length of one-time signatures.
Well, they're not on the length; they're on the number of.
On the number of Oracle queries, but it would be nice to extend that to length as well. Yeah. So I think there's a lot of work to do on these short signatures. What?
Oracle queries to what?
Oracle queries, if you're trying to prove it relative to an ideal function, the number of Oracle queries you need to the ideal function. So this is Luca's work, and then so it bounds the time, not the size of the signature. Sorry? Oh, Bosman Muhammad. Oh, that's right. Sorry. Okay, so I'm going to stop now. So basically, there are also ways to build signature schemes without random oracles. Lots of ways to do it. I'm going to skip that because I'm running out of time. And so let me conclude just by, I really liked Amit's last slide from his talk. So I'm going to steal his last slide, except I couldn't find the graphics that you used. So I had to use abstract graphics, which captures my ability to do art. So the summary of all this is, I think this is really exciting times in crypto. It's really a wonderful, wonderful field. I've been doing crypto now for a long time. I love this field. I love the community. It's a lot of fun to work with everybody. The problems are fun to think about. The world cares about what we do. So I can't imagine having any other field to work in. It's just a beautiful, wonderful area to be in. And kind of over time, essentially our power has kind of grown, right? We started with one-way functions where we can do encryption, signatures. Then came trapdoor functions, RSA, discrete log. Now we could use them for key exchange and public key encryption. Then came pairings, which allow us to do new forms of encryption, which we couldn't do before. With LWE, kind of the killer app is fully homomorphic encryption. So kind of our power grows over time. I think the revolution that we're underseeing right now is multilinear maps, and of course the killer app is I/O. But there's a ton of things we're going to be able to do with multilinear maps. This is, again, there's a lot to get out of these multilinear maps, and we're only really at the beginning. And the question I kind of have for you is, what's next, right? So what other things, do we have other things we want to build that we can't build today? And what are the tools that we're going to come up with to build those? But I/O seems to be almost every problem I can think of is solvable with I/O. Yeah. So what's next? Yeah. So what do we leave to? What's our legacy? What do we leave to our children? Like, what are they going to be working on? And so again, I would challenge the community to help our children make sure we leave the same world that we live in to our children, so that there's a hard challenge that we don't know how to solve, so that they would invent the tools to solve that challenge. Okay, and on that note, I will stop. Thank you very much.
We have time for a few more questions.
Yeah, please, Chris.
Yeah, so just a comment and a question about what you think. So in the pairing world, like all the computations are always moving forward, right? You like either have an exponent and you raise to that exponent, or you have two values and you move them forward into the target, right? And in lattice crypto, sometimes you're moving forward, then you're going backwards. Trapdoor function. Do you think this accounts for things we can do versus things we can't do, or what's your take on?
Oh, that's a philosophical question.
You even look at it that way. I mean, is that
well, I mean, I think the way I think the power from LWE comes from the fact that it sort of emulates very successfully a multilinear map, right? I mean, it's not exactly a multilinear map, but you get somewhat like that behavior, and you see that in the ABE constructions from lattices. You sort of are able, right, in the ABE constructions, you're kind of able to move from gate to gate, but you always stay within the same structure. So that's why you can keep applying what you're doing without. I mean, the noise blows up, but
in the end, to generate keys,
you have to go back.
You have to go back, right? So
Right. So you kind of well, it's kind of the best of both worlds. You get a pairing and a trapdoor. So maybe that's where the power of LWE comes from. But yeah, I don't know. I mean, every problem has, every construction has its own beauty. So can't quite generalize. Great. Yeah, please.
So I'm stuck in the past.
Yes, what?
I'm stuck in the past still.
Yeah.
So, I mean, this is incredible, right? And these multilinear maps are much, I mean, no, not multilinear. Bilinear maps, multilinear, whatever, no error, much better. But I still worry, I'm a little worried about the fact that there's one curve that everybody's using. Okay, so for example, you could say the same if there's one prime that for which we're doing discrete log and everybody thinks that that's a hard one. But there I would say choose a bunch of primes and do amplification. I forget the efficiency. I understand it's ridiculous, but choose a large number of primes. Let's say believe that there's a small fraction of primes which is hard. I'm going to use pick a lot of them, do amplification with XOR, and then say that that's pure. Yeah. So I'd like to do something similar here. But that's where I'm a little worried, because from what I know, right, if you have a curve with A and B, you know, so as you distribute the A's and B's, like AX cubed plus BX, then there's a distribution of the orders. And under the conjecture that...
If you fix the prime.
In small intervals, you'll find one that's a prime.
Yeah.
But here, you're using one curve, like y is equal to x cubed plus x, some mod p, right?
Well, first of all, there's another parameter. There's a prime, right? It's y squared equals x cubed minus x mod p. And you can you're free to choose many primes if you want. Yeah, for every prime, you'll get a curve.
Yeah, but once you chose the prime, it's a problem, because the other group, the target group, right?
No, it depends on the prime too.
No, I know. That's right, the same prime.
No. So you choose the prime, you get a curve and a target group. You choose a different prime, you'll get a different curve and a different target group.
What you need, I'm probably wrong, but it still seems what you need that you fix the prime, because you chose the prime random, and now you've got the curve. Now this is it, right? So you want to say that.
I understand the question. So let me answer it. So first of all, in practice you would actually not use the y squared equals x cubed minus x curve. In practice, you would use these asymmetric pairings, and with these asymmetric pairings, there's actually a very wide variety of curves you can use. It's not just one curve that you have to use.
Is the power, is the peak of the alpha changes, or there's more variations?
No, there's more variations in the family. So so you choose so actually the way you generate these curves is you generate the curve and the prime at the same time. You generate the two together, but you can generate many curves and primes, and each time you would get a different curve and a different prime. Yeah. Now all these pairs, you know, they give you different bilinear groups. So if you assume there's computational independence, you can amplify.
So the assumption would be that this method of choosing pairs gives me, let's say, a non-negligible fraction of pairs for which the problem is hard, the DDH problem.
That's right. Okay. So the assumption, which as far as we know is true, is if you generate one pair of prime curve and you generate another pair of prime curve, there's no reduction between those two. So it's possible that one is easy and the other one is hard.
Well, it would be better if there was a reduction, I guess, right?
Well, yeah, I guess you're right. If there was a reduction, then you could point to a hardest possible curve. That's true. But right now it's exactly like RSA. Yeah, you generate one RSA modulus, you generate another RSA modulus. There's no relation between the problems on those modulus. Yeah. Yeah, and I'm saying the same thing is here. Yeah, these are called MNT curves. There's a for every n. Yeah.
N grows large, we
Yeah. These are called MNT curves. They're a family. It's not just one curve. It's a family of curves, and you can generate. You press a button and it spits a pair. You press a button again, it spits a different pair.
Okay, sorry, MNT?
MNT curves. Yeah.
But once again, there's an issue with the alpha. As the alpha goes, as you go to larger and larger primes, that's not fully understood, is what you said, right?
Well, the taxonomy specifies it up to some large alpha, but that's gonna, in our lifetime, those are all the alphas we would need, unless there's some disaster that happens. Yeah. So I think that the generation problem is considered solved.
But is it theoretically understood? I mean, that's the question.
As alpha goes to infinity, I think it's just it's not written anywhere, but there's no reason why the taxonomy can't be extended to a larger alpha. It's just not interesting.
I thought that might be underlying what Shafi was asking.
No, but even once you fix alpha, you can still generate lots of bilinear curves. So there's quite a bit of diversity. Yeah, the family is called MNT curves. They support that.
Okay, so that's
Great. Thanks a lot.